Hello friends, we are going to learn today the Laplace formulas proof. All the proofs are done with the help of definition. So we have here definition of Laplace. Laplace of a function t is integration 0 to infinity e raised to minus st f of t dt. So let us learn how Laplace of 1 is 1 upon s. So let us see the proof based on it. We write here by definition, the Laplace of a function t is integration 0 to infinity e raised to minus st f of t dt. So in that, let us put function t equal to 1. So this will become Laplace of 1 equal to integration from 0 up till infinity e raised to minus st and into 1 dt. So we have to now integrate it. So I will rewrite this e raised to minus 0 to infinity, and e raised to minus t into 1 is nothing but e raised to minus t. Then we must know the basic integration. Integration of an e raised to ax dx is equal to e raised to ax upon a. We must remember this integration. We are going to base our integration on this. So we are going to write now e raised to minus t st's integration as e raised to minus st upon minus s with limit 0 and up till infinity. So e raised to minus st integration became e raised to minus st upon minus s. Now we should put the limit. The first limit become e raised to minus infinity upon minus s. Then e raised to 0 upon minus s. E raised to minus infinity is a value 0. So it becomes 0 minus, and e raised to 0 value is a 1. So finally the answer of Laplace of 1 becomes 1 upon s. So see, this is how we get Laplace of 1's proof. So Laplace of 1 comes out to be is equals to 1 upon s. So this is the first proof. If they ask in the examination, Laplace of 1 is equals to 1 upon s. Let us do the next part. Laplace of e raised to at. Once again, we must copy this by definition. We must first write what is the definition. In the definition, put function t. Function t is equals to e raised to at. So it becomes Laplace of e raised to at equal to the integration. I must copy the integration, same over here, same integration. The only thing I must do is change function t. In place of function t, I'll replace it with e raised to at. So e raised to minus st and e raised to at, both of them, both are exponential functions. Let us merge them together. Integration from 0 to infinity. We will have the e power written as minus s plus a and commonly t dt. So we can integrate them e raised to minus s plus at as integration answer e raised to the same minus s plus a t and divided by minus s plus a. With limits I need to put the same limit 0 to infinity. Once again, when I put the first limit, it become e raised to minus infinity and denominator minus s plus a. The second limit becomes e raised to 0 and denominator minus s plus a. We know e raised to minus infinity is 0 and minus e raised to 0 is 1 and denominator minus s plus a. So we see that the answer of Laplace of e raised to at becomes 1 upon s minus a. If we take the minus sign inside of minus s plus a, it becomes 1 upon s minus a. So this is the second proof. So e raised to at Laplace can be done like this. E raised to minus at Laplace is similar as above. You must try it yourself. to get Laplace of e raised to minus at. Like e raised to at, we have e raised to minus at. Rather, we'll do Laplace of sin at. So Laplace of sin at करते हैं. Again, we'll write by definition. By definition, we put function t this time equal to sin at, so that you get Laplace of sin at equal to, we'll copy the integration. It's the same integration that we need to copy here, but the change is going to be the function t. Instead of function t, you write sin at. Now, how are we going to integrate it? There is an integration formula of such term. Integration of e raised to ax sin bx dx is equals to e raised to ax upon a square plus b square. Then in the bracket, a sin bx minus b cos bx, a sin bx and minus b cos bx. So this is the integration formula. I'll highlight it. E raised to ax sin bx formula. We are going to use that over here. So we'll have now e raised to minus st, e raised to minus st divided by a square plus b square. In this case is minus s square plus a square. And beside that, a sin bx is going to be minus sin at and minus a cos at. So this is going to be e raised to ax sin bx ka integration 0 to infinity limit. So it's a direct integration e raised to ax sin bx, which is e raised to ax upon a square plus b square, a sin bx minus b cos bx. Let us now substitute the limit. Once again, the first limit is going to become e raised to minus infinity. E raised to minus infinity, denominator s square plus a square. And with the other term minus s sine of infinity minus a into cos of infinity. But e raised to minus infinity is 0, so eventually everything will become 0. The second part, e raised to 0 upon, it's going to be s square plus a square, and beside that in the bracket minus s sine 0 and minus a cos of 0. Okay, so we'll have this as e raised to minus infinity upon s square plus a square and e raised to 0 upon s square plus a square. But e raised to minus infinity, entire term is 0, minus e raised to 0 is 1, and denominator s square plus a square. The entire e raised to minus infinity wala part with s square plus a square minus s infinity a and cos infinity sub 0 ho gaya. What we get is e raised to 0 1, which is 1 upon s square plus a square, minus s into a sine 0 is a 0, minus a into a cos 0 is a 1. Cos 0 is a value 1. So if we simplify them more, okay, just a moment please. Now, if we simplify them more, it becomes equal to minus minus plus a upon s square plus a square. So this is Laplace of going to be sin at a upon s square plus a square. I'll highlight this. A upon s square plus a square. Now similarly, Laplace of cos at can be done. Again, this is homework for you. I will only mention here the integration formula. The difference is going to be the integration formula e raised to ax cos bx dx. It has an answer e raised to ax upon a square plus b square, and in the bracket a cos bx plus b sin bx. So that is a difference in the formula. Otherwise, it is same integration. I'll highlight this. So last time we had used e raised to ax sin bx. Now we have got to use e raised to ax cos bx. So I leave this as homework for you so that you can try yourself. Coming to the sixth proof, sin h at. Now we don't have to go by definition to prove sin h at. Sin h at can be proved very easily. Let's see how that is done. We write Laplace of sin h at is equals to. We know that sin h can be converted into e raised to at minus e raised to minus at and upon 2. Now how is that? This is also a formula. What formula is that? I'll write here sin h theta's formula. It is equal to e raised to theta minus e raised to minus theta and upon 2. This was the sin h conversion. This is trigonometry, Euler's formulas conversion, sin h theta. So we use that over here. So we write it as is equals to 1 upon 2 outside Laplace of e raised to at minus e raised to minus at. E raised to at and e raised to minus at Laplace is already known to us. 1 upon 2 into 1 upon we can write s minus a minus 1 upon we can write s plus a. So we don't need to integrate this time. It can be easily done with this. So we write equal to 1 upon 2. On cross multiplication, we get s plus a minus s and plus a, and denominator is s minus a into s plus a. We see the numerator minus s and plus s cancel out. We get the numerator 2a, and the denominator s minus a s plus a is s square minus a square. So half and 2 can cancel out, and eventually we get our answer Laplace of sin h at, Laplace of sin h at is equal to a upon s square minus a square. So this is the Laplace of sin h at we have got. Similarly, one can do Laplace of cos h at. Fifth, this is an homework for you. You can do it yourself. I will only mention here the cos h formula. Cos h theta's conversion is equals to e raised to theta plus e raised to minus theta and divided by 2. The way we had sin h theta's formula, this is cos h theta's formula. Sin h theta and cos h theta's formula. So you can try yourself how Laplace of cos h at is s upon s square minus a square. Now regarding t raised to n, how to find out Laplace of t raised to n? Let us do it. This is done by integration. Let's see how that is done. By definition, we write it. I'll take it from here. By definition, 0 to infinity e raised to minus st f of t dt. We have to put function t is equal to t raised to n. When you substitute that here, it becomes Laplace of t raised to n, which is equal to integration with 0 and up till infinity. 0 to infinity e raised to minus st into t raised to n dt. Now we have to use here gamma functions concept. I'll remind you how that is done. We have to put the power of e st is equals to say some new letter x, so that t becomes t is equals to x upon s. Okay, just write this tab properly. Just a moment, please. Yeah, just get the tab proper. Okay, t is equals to x upon s, so that when you derivate, it becomes dt is equals to dx upon s. So now we come back to the question. Laplace of t raised to n is equals to, again writing integration from 0 up till infinity, because limit remains unchanged. E raised to going to become minus x into t raised to n is x upon s raised to n. Dt is dx upon s. So we have substituted in place of st x, in place of t x upon s, and in place of dt dx upon s. Let us solve it further. I'll just adjust the tab. Let us solve it further. We see that we can take constants outside. I see a constant 1 upon s raised to n out. I even see a constant 1 upon s out. After that, I can write integration with the limit 0 up to infinity. And inside that, I have the term e raised to minus x, x raised to n dx. Now this has become gamma definition. On the outside, we write 1 upon s raised to n plus 1 power. And what this has become is a gamma function. This is a gamma function. Gamma of n plus 1. This was the definition of gamma. 0 to infinity, e raised to minus x, x raised to n is gamma of n plus 1. This is what we have learned in the maths 2. Diploma students haven't learned in the maths 2, but they can now take it directly. All integration of this category, 0 to infinity, e raised to minus x, x raised to n dx is actually gamma n plus 1. So we have got the answer, Laplace of, so we have got our answer, Laplace of, I'll just write the answer, Laplace of t raised to n is equals to, the numerator is gamma n plus 1 and its denominator s raised to n plus 1. Also, gamma n plus 1 can be written as n factorial and s raised to n plus 1. So both ways can be written. It can be written as a gamma function. It can also be written as a factorial function. So this is what we get Laplace of t raised to n. So these are all the 8 formulas of Laplace we have learned.